Good morning. My name is Vignan Alaki Ramamurthy, DE190011. So I will present about introduction, filler table, and flowing chart for the PBL activity 1, which is topic about noise. For the introduction, noise is defined as anything that disrupts the communication process between a speaker and an audience in communication studies and information theory. Interference is another name for it. Noise can come from the outside as a physical sound or from within as a mental disturbance, and it can interrupt conversation at any time. Noise also can be seen as a factor that diminishes the probability of successful communication but doesn't not guarantee failure. Noise is a term used to describe an undesirable disruption in an electrical signal. The disruption can be caused by electronic, thermal, quantum, impulsive, or intermittent dilation noise are among the type of noise. Noise levels can be affected by environmental factors such as temperature and humidity, while the signal-to-noise ratio is abbreviated as SNR or S/N is a measurement of the strength of a desired signal compared to the background noise or an undesired signal. Sn is determined by comparing two levels and calculating a ratio that indicates if the noise is interfering with the desired signal. In this first problem-based learning assignment, we are given a problem to answer which is about noise. We are asked to offer a solution that produces the maximum signal-to-noise ratio output of the communication system based on a few constraints and conditions. Furthermore, regardless of the condition and limits imposed, we must develop numerous techniques to improve the output of SNR by integrating the pieces of the knowledge and inputs we got from the classes with the research we conducted. We have completed the PBL assignment. For the filler table, for the amplifier, the ideas we came out with is to design a new amplifier, and the learning issue was how may the signal amplitude and SNR can be improved. And the action plan was taken was a summing amplifier is used in the system. And for the receiver performance, we came out with the idea where the signal optical power reaching the receiver should not be less than 35 dB, which is decibels. The learning issue was how can the optical power of a signal reaching the receiver can be controlled. The action plan was taken was minimize the signal optical power reaching the receiver. For the reducing noise generated by the amplifier, the idea was internal noise is caused by thermal effects in the amplifier, and while it can be reduced, it cannot be fully eliminated. What was the learning issue was how can the noise be reduced. The action taken was amplifier that match the input signal bandwidth will be less noisy. For the amplifier load, the idea was to use the advantage of using of cascade amplifier. The learning issue was is it better to use a cascade or a cascade amplifier? So the action taken was we used a cascade amplifier. So to noise error in the signal, the idea was to reduce the noise reduction. So the learning outcome was what is the most effective method for the filter to out the noise. The action taken was a low pass filter is used. So lastly, the arrangement of the cascade amplifier. The idea was to prevent noise from increasing at a quicker rate than the signal. So the learning was what can be done to keep the noise from getting louder. The action taken was each stage of the amplifier must be run in a linear mode. For the flowchart, first we start the experiment by using the formula SNR SI equal to NI. The second step was use the initial parameters of the amplifier and chamber. Third, we calculate the noise temperature with the formula TE equal T1 plus T2 over G1 plus T3 over G1 times G3. Then we obtain the noise factor of three different chambers with the formula F equal to F1 plus TE plus over T. Then we calculate the total noise figure Ft with the formula Ft equal to F1 plus F2 minus 1 over A1 plus F3 minus 1 over A1 times A2. Then we calculate the SNR output by using SO equal to NO or equal SI over Ni minus NFT. Then we compare the SNR output. If it is small, we adjust the chamber temperature and relocate the amplifier, and we go back to the step where we calculate the equivalent noise temperature formula. If it's big, we record the maximum SNR output produced and the chamber's temperature and location of the amplifier. And that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azam bin Hassanal. Metric number CE200025. I will present the second way. We adjust the equivalent noise temperature of the chamber one to a lower temperature. As assume, I will take 346 Kelvin because the chamber one equivalent noise temperature varies. So we simply need to recalculate the noise factor, organize the cascade amplifier, and calculate the overall noise factor and output SNRO presently. So the noise factor chamber one, we put F1 equal to 1 plus 346 Kelvin over 308, and we got 2.1234. As a result, the cascade amplifier is in the following order: amplifier 1, amplifier 2, and amplifier 3. Uh, and next, the overall noise factor of numerous cascade amplifier is then calculate using the Friis formula. The Ft equal to F1 plus F2 minus 1 over A1 plus F3 minus 1 over A1 times A2. So we got 2.1234 plus 0.185 plus 0.0232, and we got 2.13318. So so for the output signal to noise ratio SNRO, we calculate we got the SNRI is equal to 1.8233 times 10 to the power of 12 over 2.13318, and we got 1.2108 times 10 power of 12. For the SNRO in dB, we put the uh, 1.108 times 10 power of 12 to, into the formula. 10 log 1.1 1.2108 times 10 power of 12, and we got one uh, 120.8307 dB. For the third way, we only change the equivalent noise temperature of the chamber 3 to the smaller temperature, which is we use assume 300 Kelvin, and then we calculate the same with the the second way. We just need to recalculate the noise factor, arrange the cascade amplifier, and calculate the total noise factor and output SNRO. Thus, for the F3, we put into the formula is equal 1 plus 300 Kelvin over 308. So we got 1.9740. Therefore, the cascade amplifier will arrange as amplifier 3, amplifier 1, and amplifier 2. So for the total noise factor, the F3 plus F1 minus 1 over A3 plus F2 minus 1 over A2 times A3. So we got 1.9740 plus 0.1136 plus 0.0117, and we got 2.0993. So the output signal ratio, we put SNRI over our total noise factor. We got 1.3449 times 10 to the power of 12, and we put the in the SNRO 10 log 1.3449 times 10 to the power of 12, and we got 1.2 point 1.1.2869 dB. That's all from me. Thank you.
Assalamualaikum and good afternoon. My name is Ahmad Shafiq bin Ahmad Sunusi. My matrix number CE200118. So today I will present for assignment 1 for PBL1. So uh, I will present for the fourth way from this assignment. So on this method, we need to recalculate both of the noise factor and rearrange the escalate amplifier. So firstly, we calculate the total noise factor and output signal noise ratio. So firstly, we want to find the noise factor for chamber 2 and chamber 3. So this is the formula for want to find the factor. Chamber 2, we have the 360 Kelvin here, and we using this, and the answer here. Chamber 3, the formula is here. We using for 450 Kelvin here, and inside the formula, and this is the answer. We get for this Kelvin chamber 2 and chamber 3 on this formula. I will show you this. We all together to find the answer for this formula. Then so next is we calculate the total noise factor several cascade amplifier by using Friis formula. So this is the Friis formula. Firstly, we want to find the total for noise factor here. So F3 for the chamber 3 here. We get the answer from here. Factor 3, and this a factor 2, and this again 3 here. Here 10 gain, and here the gain 2 and gain 3, 40 and 10. So this the amplifier 1, factor 1. So the answer is here. Okay, next we we do the output signal to noise ratio. This is the formula. From this factor total, we insert in here formula, and we got this. And then next and final step, we using the 10 log to find the dB. So this answer for the output signal, we insert in here 10 log here, and the answer is 120.1185 dB. So the fourth way, the output for signal noise ratio is the 120.118585 dB. So this is the answer for fourth way. That's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Doctor, today I want to present question 2. Without considering the method, condition and limitation, what could you propose for further enhance the output SNR? Discuss and elaborate. Firstly, I received the signal power in input and output of the system can be higher. Input signal to noise ratio SNR1. The formula is SI over SN1. Input signal to noise ratio SNR1. The formula is SNR1 divided by FT. SNR output depends on SNR output of the system. So, when the data increase receiver signal power SI to a higher value will automatically enhance the SNR. 2. Using a cascade amplifier. A cascade amplifier is a two-part quad network designed with an amplifier which are connected in series. When every amplifier transmits its output to the second amplifier input in a daisy chain. The problem is measuring the gain of the cascade stage on the non-perfect compiling among two stages because of the loading. The two stages of the cascade CE common emitter are shown in the following circuit. Here the voltage divide can be formed by using the input and output resistance of the first and next stage. Next is third, redesign the standard amplifier. When designing amplifier circuit, the class of operation of an amplifier is very important as it is determine the amount of transistor biasing required for its operation as well as the maximum amplitude of the input signal. Amplifier classification take into account the portion of the input signal in which the output transistor conduct as well as determination both the efficient and the amount of power that switching transistor both are consumed and dissipate in the form of waste heat. Here we can make a comparison between the most common type of amplifier classification in the following table. Using summing amplifier in the system will be improved the signal amplitude and also SNR value. In the summing amplifier, it is the summing of the uncorrelated and correlated signal. The benefit of parallel design in amplifier, it also improves the SNR value and lower the voltage noise density of the system. Thank you from me. Assalamualaikum.